Metal erosion is a costly problem. It attacks pumps, valves, piping, and other expensive equipment. No matter what type of liquid is being used, there's always the risk of damage from flashing and cavitation. Wherever there's a restriction in flow, the decrease in pressure can cause a fluid to reach its vapor point. Flashing occurs when the fluid vaporizes and remains a vapor. Metal erosion caused by flashing appears smooth and shiny. Cavitation occurs when the fluid vaporizes, then returns to a liquid state as the pressure increases downline. The metal damage caused by cavitation is rough and irregular due to pitting of the surface. Cavitation is a major source of damage in control valves and other components. Cavitation occurs as a liquid passes through a restriction, such as a valve. The restriction causes the liquid's velocity to increase and its pressure to decrease. The point of maximum velocity and minimum pressure is called the vena contracta. Vapor bubbles form in the liquid when the pressure falls to near the level of the liquid's vapor pressure. When the pressure recovers downstream, the vapor bubbles implode and return to liquid form. After the initial bubble formation and collapse, the bubble may reform and collapse a second time. Liquid microjets form when the recovering pressure makes an indentation in a bubble. Then the microjet bursts through the bubble. These implosions can also cause local pressure waves of up to 100,000 pounds per square inch. The combination of pressure waves and microjets can cause severe damage to the valve plug, seat, and body when they're located near the material surface. Cavitation can also cause unacceptable noise and vibration that reduce efficiency or lead to loss of process control. Even though cavitation occurs, it doesn't always cause damage. The extent of cavitation damage is affected by the following factors: the intensity of the cavitation. Greater drops in pressure increase the potential for damage. The materials used in the construction of the area where the cavitation occurs. Hardened materials reduce damage. The length of exposure to cavitation. The more frequently that cavitation occurs in an area, the more likely it is to sustain damage. Valve size. Increasing the valve size tends to make the effects of cavitation worse. The design of the valve and trim in the area of cavitation. High recovery ball and butterfly valves are more susceptible to cavitation damage. If there is leakage occurring when a valve is closed. Fluid leakage moves fluid from a high-pressure area to a low-pressure area, which results in cavitation and potential damage. Cavitation damage can be reduced by altering or accommodating any of these factors. Cavitation damage can often be reduced or prevented by using the proper components. Emerson offers these solutions. Valve liners are constructed of hardened materials to protect the valve body. Pressure staging keeps the pressure from falling to near a liquid's vapor pressure, which helps prevent vapor bubbles from forming. Pressure drops are staged by the use of expanding nozzles or expanding flow areas. For example, in the Cavitrol 3 valve trim, nozzles have holes shaped to manage flow separation. Multiple small holes shift the noise to higher frequencies. Cavitation is isolated by directing fluid into the center of the valve using a flow-down orientation so bubbles implode away from the valve components. In addition, the Cavitrol 4 valve trim has expanding flow areas that decrease pressure as the fluid flows through. Limits changes in pressure at each step to prevent fluid from reaching the vaporization point, and prevents leakage. Fisher Control Valve Technology from Emerson Process Management provides customers around the world with leading critical valve solutions. You can count on Fisher Products, backed by its 125 years of valve development and manufacturing experience, to solve your critical valve needs.